Yeah, so in this question, so they're telling consider the situation shown in the figure. So this is a figure for this question, 68 question. So here they're telling the plates of the capacitor have a plate area of A. So they're telling area of this plate, okay, so area of this plate is A and are clamped in a laboratory. So the dielectric slab is released from the rest. That means initial velocity is obviously like, let us assume that initial velocity is what? 0. So because they're telling it's released from rest and within a length with a length a inside the capacitor. So you can see that a length of this slab is inside the capacitor, neglecting any effect of friction, okay, and or gravity. So you shouldn't be bothered about the friction or gravity. So then show that the slab will execute a periodic motion and find its time period. So they're telling that, so they're asking us to find or like show that it is like performing what, periodic motion, and then also if it is performing periodic motion we need to find what, time period. So let us try to analyze what happens to the situation, why it should be attracted. So let's say here actually we know that this is connected to like higher potential and this plate is connected to higher potential, this plate is connected to lower potential. So let's say here we have positive charge on this plate like this, and here we have negative charge on this plate, and we know so how the charge will be induced inside the dielectric, right? So basically here on this like higher potential plate positive charge, and here we will have negative charge, and on the dielectric we know the charge will be induced. How the charge will be induced? Here you know minus 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 charge will be there, and here plus 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 charge will be there. So because of this you can see that these negative charges will be pulled, okay, pulled by this positive charge, and this positive charge will be pulled by this what, negative charge. Then you might be thinking, sir, why this negative charge won't be reflect like what, repelling this negative charge? Means yeah, they'll repel, but compared to this negative charge these positive charges are closer, so attraction is more than what, repulsion. As a result this slab will be attracted towards this. But imagine if they clearly mention the length of the slab is what, L. It's very very important over here. So when it is completely inside this capacitor, then no force will be there, okay. So then no force will be there, because so it will be just cancelled, it will be equal and opposite, then it will be cancelled. But now so it will be something like this. So therefore the vertical component of the forces will get cancelled, but there will be a resultant force in what direction, horizontal direction. So that means you need to understand, so till the time the slab comes completely inside the slab, obviously it will be dragged, okay, dragged towards or like dragged into the capacitor. And once it comes over here, then net force becomes what, zero. Then net force becomes zero. But then you need to understand that, okay, then you need to understand that, so from here to here as there is a force, it like it's been accelerating, okay. Whether it is a uniform acceleration or non-uniform acceleration, that we'll see later, but it's accelerating, right? All the time the force is like what, the net force is towards left. As it is accelerating, by the time it's reach over here it will be gaining some velocity. So because of its inertia, now suddenly even the force is becoming zero, it cannot come to rest. Even though the force is like what, zero, when it is completely inside the dielectric, you need to understand that it cannot come to what, rest. Then what will happen? So because of inertia it will try to move outside the capacitor. Now it will try to go slowly like out of the capacitor, but when it started moving left side, then there will be like what, attraction again towards what, towards the capacitor. Then again slowly it will be like what, decelerated, its speed will decrease. But then you know that as there is no friction, no like gravity, there is no loss of energy, and we know that energy in the capacitor will be stored in the form of what, electric field. So as the energy is stored in the form of electric field, and we know electric field is a what, conservative field, right? So conservative field, so that means no energy will be lost, just energy will be stored in the form of what, potential energy or like kinetic energy of the system. But we know that energy is, as it is in conservative field, energy cannot be what, lost. So that means, so till where it will go, so till where it will go means you just need to understand, again it will go till a position of what, because it should be storing the same amount of energy, that means same capacitance should be there. So sir, how can we get the same capacitance, like even though the like dielectric is going other side? Obviously again if the dielectric is in such a way that A length of the dielectric is inside the capacitor, it is same as the original given system, right? Then that is the position where it goes to what? Rest. Again it will be like repeating, right? So then again its velocity became zero, but now it has a force towards like what, center of the cap, like towards the capacitor, and then again it will be accelerated and it will be coming to like completely inside the capacitor. Then net force is non-zero. Okay, sorry my bad. The net force is zero, but its velocity is non-zero because from there to like here it's been accelerating, so it gained some velocity, and because of inertia it will continue to move towards right. Again till where it will go, whatever the original position is there, till that position it will be going. Okay, so that means, so I hope you understood without writing any equations. Okay, just by knowing the like kinematics, or like kinematics basics clear. Okay, if your kinematics basics are clear, so without solving anything we can just conclude that so this will be executing what, a periodic motion. Okay, this will be executing a periodic motion, because from here it will go back to this position, again it will come back to this position, again it will go back to this position. It will be keep on repeating that. Okay, so I hope it is clear why it will be a periodic motion. Okay, so and one of the key point here, the most important thing is, as the electric field is conservative, no energy is lost, so that means it should be having the total energy of the system should always remains what, constant, right? So now, so let us try to write the energy, or like the capacitance. Okay, first let us try to write the capacitance here. So let's say imagine at some instant x distance of dielectric is inside. Okay, let's say imagine that at some instant how much length of the dielectric is inside. Imagine x length of this one is inside. Okay, if x length is inside, now let us try to write this capacitance. Now you need to understand that, so we can divide this entirely into what, two capacitors. So this is our C1 capacitor and this is what, C2 capacitor. C1 capacitor and C2 capacitor. Now this, when this length is x, the remaining length would be what, L minus x, and they have given the complete area is what, complete area is A. Okay, so if this length is so if the area of the plate is A and this length is L, that means you need to understand that, so inside this plane this length should be how much, this length should be obviously A by L, because the total area should be how much, total area should be A, area of the plate is A, so this length is A by L and this length is L, then you will be getting the area A, whatever the area of the plate that is given. That means this, whatever the length into the plane, okay, that we can see, it will be how much, A by L. Now, and one more thing, as the battery is connected for this top plate and bottom plate, you need to understand that this capacitor and this capacitor, how they are connected, obviously they are connected in parallel. Why? Because they are connected across the same potential difference. As they are connected across same potential difference, that means this plate and this plate has same potential, and this one it's completely a single plate, right? So this is, let's say this plate is named as M potential and this name is named as N potential. So this capacitor is between Mn potential and this capacitor is also between Mn potential. As they are across the same potential difference, obviously we can consider those two as what? We can consider those two as like parallel. So when capacitors are in parallel, you know, C equivalent will be written as what? C1 plus C2. So then C equivalent equal to, what is the formula for capacitance, parallel plate capacitor? A epsilon naught by D. So what is the area of this plate? Length is L minus x, and into inside, like what is the length to inside the plane? A by L. So this is A epsilon naught by distance between the plates. Distance between the plates is given as D, plus C2. When dielectric is there, the capacitance will become what? AK epsilon naught by D. First of all, what is area? X into A by L into K, AK epsilon naught by N, by how much? D, right? So now let me write the C equivalent here. C equivalent. So the C equivalent would be how much? The C equivalent would be L minus. So what are the things that I can take common? You can clearly see that I can take A epsilon naught by dl common. Once I take A epsilon naught by dl common, what will be left? We will be left out with L minus x plus kx. So this will be the capacitance, right? This will be our capacitance. Once we know the capacitance of the capacitor as a function of x, now at any instant, okay, like at any instant of time, so we can also write the energy stored in the capacitor. Okay, we can write energy stored in the capacitor. What will be the energy stored in the capacitor? Half C V square, where V is not velocity, V is the potential difference across the plates, which is also a constant value, which is given as what? E. So then what we can write? Then we can write it as half, what will be C equivalent here? A epsilon naught by dl into L plus x of what? K minus 1 half C E square. Okay, so this EMF is given as E. So now this is the potential energy, or like energy stored inside the what? Capacitor. So this energy is stored in the form of what? This is the most important thing. This energy, whatever this energy is there, energy is, so you know that in the capacitor energy is stored in the form of what? Stored in the form of electric field. In the form of what? Electric field. So electric field, you know, it's a what? Electric field is an conservative, right? So as it is a conservative field, so then we know the relation for potential energy and force, right? Whenever we have conservative fields, so electric field here is what? Electric field is conservative in nature. So then we have a relation for the force, okay, the conservative force, the relation between conservative force and the potential energy. So what is the potential energy? F equal to what? Minus du by dx. F equal to what? Minus du by dx. So this minus sign here indicates like what? The direction. Okay, so but if I just want magnitudes, I'll just keep mod on both the sides. I'll just equate the magnitude of the force to what? Like differentiation of this energy with respect to what? X. Now let us try to differentiate the whatever the value of u that is there with respect to x. So this value, let me differentiate with respect to what? X. So this is the value that we are having. Now let us find du by dx. So what will be value of du by dx? So we know that a epsilon naught e square by 2dl is constant, and differentiation of L with respect to x is what? 0. It's a constant, and dx by dx is 1, so you'll be getting k minus 1. So therefore the conservative force, F electrical force, the conservative force is given as what? A epsilon naught e square by 2dl into how much? K minus 1. So this is our force. This is our force. And you can clearly see that it is independent of what? Independent of the x. Okay, you can clearly see that this is independent of what? The force is, this is independent of x. Okay, that means here we got some important point. So what is the important point that we got? The important point that we got is force on the slab is independent of length of the slab inside the capacitor. Independent of length of the slab inside the capacitor. So now, so already we have proved, okay, like starting of the discussion itself I have told. So what I have told? So I have told that it's a periodic motion. Now they are asking time period for this periodic motion, right? So how to find time period of periodic motion? Already I told you how the motion would be, right? So basically, if this is the capacitor, okay, initial given situation is something like this. So what is the initial given system? So it is somewhere over here, and then it will be coming till over here, and again it will be going back to this place and this point, right? So that means, so from here to here it is, let's say, t time, and then you need to know from here to here also it will take what? Again t time, and from again here to here again it will take t time, and again from here till here it will be taking what? T time, right? So basically it's like 4 equal sections of time period. So therefore let me calculate the time taken for the body to go from extreme position to what? Equilibrium position. So time taken by the particle to go from where to where? Time to go from extreme to where? Extreme to equilibrium. Equilibrium position means what? Net force 0. So when the net force is 0, when the slab is completely inside what? When the slab is completely inside the capacitor. Okay, so then that means, so then as we got the force is constant, when the force is constant, obviously the acceleration will be constant. So when the acceleration is constant, then we know you can use equations of motion, right? So therefore acceleration is nothing but, acceleration of the dielectric is nothing but F electric force divided by what? Mass m. So as the acceleration is constant, I can use what? As F is constant, A is also constant. As A is constant, we can use what? We can use equations of motion. Okay, so equations of motion, what I'll be using, initially it started from rest, right? Obviously to what length it will be going. So to what length it should be going means from here, so this total length is L and this is A, so that means remaining length is what? L minus A. So that means it should be covering a distance of how much? L minus A distance it should be covering, right? So therefore what we can write, which implies as initial velocity is already 0, so I'll be using the formula S equal to ut plus half a t square. As I said, S equal to what? L minus a, and which is equal to half into acceleration, already I got F electrical divided by what? Mass m into t square. So therefore t equal to how much we are getting? Under root of 2m into L minus a, 2m into L minus a by F electrical. And this is the time taken for the particle to go from where to where? From extreme till equilibrium, right? But they are asking us to find total time period. So therefore the final conclusion is what? Total time period. Total time. So what will be the total time? Total time equal to 4 times t. As I said, for the 4 sections it will take the same time, right? So therefore what will be the total time? So the total time would be 4t. The total time will be what? 4t. So I hope it's clear. Okay, so this is the last question in H.C. Verma in the capacitors chapter, right? Okay, yeah, thank you, bye bye.